Thank you for staying. Such a late presentation. I know that you're here just because of the raffle and the beer, but I choose deliberately to ignore this fact. So thank you very much for staying, and let's get to the presentation named Performance Testing Done Right. A little information about me. So my name is Jiří Holusia. Don't worry about the pronunciation of the name. You know, I'm used to Jiří, Siri, Jiri, whatever. And seriously, even in my own company. And I work at Hazelcast as a quality engineering team lead. Besides that, I'm a true Czech person, so I like beer. I love beer. So kudos to the organizers. Perfect job done for me. I'm very happy with that. So just a little motivation for the beginning. In Hazelcast, so just a little show of hands. Who's familiar with Hazelcast? Heard of it? Used it? Okay, sounds good, perfect. By the way, for this presentation, no knowledge of Hazelcast is needed. I was just curious. So at Hazelcast, we do three products, basically. We do, the most known one would be in-memory data grid. Long story short, distributed cache. We do Hazelcast Jet, which is a stream processing library. So again, fast stream processing engine. And Hazelcast Cloud, where is a managed service of the Hazelcast IMDG. So, you know, distributed cache, fast processing engine, etc., etc. So all we care about is performance. If we're not fast, then we're completely useless. Nobody will ever install slow cache, right? That's what not the cache is for. So we pay close attention to performance at Hazelcast. We test it as much as possible. And during my days in Hazelcast and also in Red Hat, when I was working on Infinispan, I was still seeing those same patterns or same glitches that can be done better during performance testing. And I would like to focus this presentation not only obvious things like the warm-up. I'm not going to talk about that we have to do warm-up of our applications when we're doing performance testing, because the JIT compiler will kick in and it will optimize everything and it will then become so much faster. Now, everybody knows that. This is a room full of very skilled developers. I know that this is an awesome conference, so I'm not going to say a word about warm-up or stuff that everybody knows. So let's try to focus on some other maybe non-obvious but still trivial things to notice, to get right. Before we start, just 2 slides about the terminology so we would be on the same page. So in performance testing, we have 2 basic metrics for describing the performance of the system. First of all is the throughput, which is a number of operations per time of unit. Number of operations per second, the typical example. And the other one would be latency, or AKA response time, which is a time from starting the request, or sending the operation, invoking the method, whatnot, to actually getting the response. Sending a REST call, calling a method, sending sending the value over the network and getting the value back. This is the operation, and we're measuring the latency of it. The other thing that I would like to get straight up now is the type of the performance test. This division is this is kind of my division, and I will just try to justify it in front of you in the talk. But I divide it into 2, let's say types of tests. That would be the first one would be the performance test, the real performance test for throughput and latency test, which you actually get the numbers, where you compare the numbers that you get as a result. For throughput test, obviously, the higher the throughput, the better. We're trying to get or execute as many operations as possible. And for the latency test, we fix the throughput and then measure the response time for the single operations. I will talk about it later as well. And there is another category called stability, I call it stability testing, but it's also it's some well-known literature. So the output of that test is when we're trying to push the system to the limits, and we're observing whether it's stable, if it can hold up to that particular load. So, and the answer is yes or no. Okay, the system will remain stable. Or no, the same system will crash, the JVM will crash, we have a memory leak, whatnot. So this is the basic divisions that I will be operating through this presentation. So The presentation is structured in the following way. I will present 5, let's say, problems or maybe things to think about. I will always describe it, then show an example of it, either chart or some table result, something, and then propose a solution or give a takeaway, how to avoid it in the future, or just think about it. So let's get started. I like to start with the problem. I like to use metaphors. So I'm actually getting married in two months, and people, from my point of view, I think that the life before the marriage and after the marriage will not be different. And every single married man will tell me that I'm wrong. So I need not distinguishing between those before and after. Okay, maybe I'm wrong. Maybe I will tell you that I was wrong, in 2-3 months. So let's not do the same the same problem, the same mistake during performance testing. Let's distinguish between those two categories. Would be latency test and throughput test. Why? Because what I see very, very often is that the people, the engineers or the testers or whoever, execute the throughput test and then look at the latencies and compare the latencies between them. Why is that not a good idea? I'm not saying that it's completely useless, but why isn't it a good idea? When you're doing a performance test, you will always get fluctuations of the results. You will execute it for the first time, you will get 100 operations. Then you will execute it on the second time, exactly the same setup on exactly the same machine. You will get 105 operations. Then you will have 97 operations, etc., etc. So if the throughput is actually fluctuating, so how can you, take a look at compare the latencies between each other? Because one of the parameters is actually moving. So that's the problem that we kind of need to think about. And we do this, I was always wondering why we're doing this. And the thing is that latency and throughput are very often related. The lower the latency, the higher the throughput. Because if one operation takes lower amount of time, I will be able to make, more operations, obviously. It's basically an inverse, and vice versa. This holds true mostly for single-threaded applications, almost all the time. But in a concurrent, especially in the concurrent environment or distributed environment, this might not hold up. And let me show you an examples of optimizations, or that you, let's say that you're developing a feature or a performance optimization when you're trying to do implementation number 1, implementation number 2, and then you want to compare which one is better to decide which way to go. So one of the first optimization you might do. So on the left column, you will see sending queries, sending operations, and we're processing them as they come. Query number 1, query number 2, 3, 4, and they take different times, right? Obvious, the simplest thing you can ever do. So what about we did some kind of time-sliced round-robin fashion, that you actually have a fixed time slots and you're executing the operation, and if it finishes in the time slot, good. If it doesn't finish, you pause it, you move to the other operation, and then come back to it. So this is exactly what's on the right side. From this diagram, what we see, obviously, is that the throughput will remain the same, right? It will not get better. But the latency might get better, actually. The latency, for instance, for the queries 3 and 4, I see that the time that they finished is much, much earlier. And for queries 1 and 2, it's, let's say, slightly worse. Slightly worse. Of course, it depends on the specific use case. But this optimization might actually improve your latency and do nothing to your throughput. Actually, it might make your throughput worse. Obviously, because the pausing the operation and restoring in and moving to another and pausing in, etc. It's an overhead. It's an overhead that you're not actually executing the operation. You're doing something on the infrastructure. So you actually might get worse throughput with better latency. Suddenly, it doesn't hold up. Let's try the other way around. A typical example when you want to get better throughput and do not do anything to latency is a web server. You have one response thread, okay? And if I had 10 threads and I haven't done anything to the thread, like I haven't optimized anything in that thread, so that means the thread will always, it will be serving the request still with the same latency. But now I can do 10 requests in parallel. So obviously increasing the throughput. And again, because I'm putting more load on the system, the latency will probably get worse because the system might get under bigger pressure. So that's the other way around. You get the better throughput and worse latency. So this is what I wanted to show you, that the intuitive meaning that the latency and throughput always correlates, it's an inverse one of each other, does not hold all the time. So what's the takeaway? I call it the solution, but it's not a solution. It's the takeaway. It's what you should be thinking about. Is that when you're actually trying to, you're doing an optimization, and you should think of, okay, this optimization will do. I expect that latency will go down, up, whatever. The throughput will, change in that way, and you should test it separately. You always want to isolate as much as possible the things that you're testing, because the more parameters are changing, the more fluctuations you get. And it can always, if you get better fluctuations, it may lead you to the wrong direction. You have two implementations, and then you choose the other one just because you didn't fix the throughput. Computers have bad days. Sometimes sometimes perform 50 operations, sometimes 100. Sometimes your very happy colleague will run background to the process there, and you don't notice. So it happens. So that's the first takeaway. Distinguish. Think about what you're testing, what you're developing, or what you want to test. So problem number 2: inadequate load on the system. So have you ever, I might use my fiance in this presentation a bit too much, so please don't be offended. So have you ever heard that, like, you asked, what is something happening, something wrong? No, nothing. It's a trap, It's a trap. We all know it. It can lead you into bad directions. So what I mean in the performance point of view is that putting an adequate load during the testing is very important. You cannot just put, like 10 stressor threads or 100 stressor threads just like, I'll put 100 because I like the number. And why? This is the why. So if you're pushing the system over the limit, the system will probably do a lot of context switching. It will be overwhelmed, and you're actually not testing your optimization anymore. You're testing how the system behaves. You're testing its stability. So it may again lead you in the wrong direction. The same thing goes when you don't stress the system enough. And let me show you again examples. So this is an example. I hope it's kind of visible. I didn't want to nicer the charts, because these are some of the charts that are actually generated using Hazelcast. So what it shows, the red line, this one is we have 8 clients on one machine. You don't have to know the details, but the thing is that, okay, I have 8 stressor entities on one machine. I put 16 on them. Okay, the throughput increases. It scales. Hazelcast scales. We're great. And then you put 24. It doesn't scale anymore. So the first hypothesis is like, okay, the servers are not able to keep up anymore. There's a valid hypothesis. But if I actually try to use those 24 clients on 2 machines, 12 and 12, the throughput is right there, is the pink line above, right there. I'm a volleyball player. So yeah, so this hypothesis is not correct. It's not a server mistake, it's a client mistake. And what we found in this particular case was that on the client machine, there were so many threads on the one client machine that the threads were actually fighting over the resources. They were doing context switching, so not doing anything useful. Thus, not performing as they could. So this actually might mislead us again, because if we're doing some optimization on the client side, we don't see the effect of our optimization. We see how the client behaves under extreme load, extreme stress, hiding the effects. The numbers that we saw here, spoiled. The numbers that we saw here were actually hiding the optimizations behind it. Let's try it the other way around. I told you that the not enough load might be misleading as well. So this is another chart. Very similar scenario. We have one client. Our Hazelcast clients are highly optimized for multi-threaded environments. So we have four clients on that one machine, each driven by just one thread, one Java thread. And the blue line is that we have just one client operated by 4 threads. So in total, we have still 4 threads to be stressing the cluster, stressing the members, stressing the servers, whatnot. So 4 and 4, it should be the same. You see the drastic, it's more than 200%. It's a drastic difference. Why, you might ask? I can give you our explanation for that. Because Hazelcast client is very optimized for a multi-threaded environment. We have thread pools there. So for I/O I/O receive thread and I/O response thread and operation thread and computation thread. So we had those thread pools, and every time the message comes at one thread pool, that it handles to the other, and then it handles to the other, and it creates a lot of threads. And what was actually happening in this particular case, that the one client created all those thread pools, but the threads were not busy enough. So what the thread does, for instance, the I/O thread, it received something, nothing to do, let's go to sleep. Wake up, okay, here's nothing, go to sleep. Wake up, go to sleep, wake up. So not doing any useful work. This is the key point, that we were not stressing our software to the optimal level of performance. And I'm talking, it's a completely valid scenario. For instance, if a customer wants to use it like this, go if you want. It's a bad idea, but if you want. But when you're trying to decide, as a developer, if you want to try to decide whether your implementation or your optimization is better or worse than the other one, you actually want to have the good numbers. You have to test the optimization, not the things around it. So the only takeaway, the takeaway from this is to actually get to know your software, to actually understand how your software is designed and how it behaves from a performance point of view. And the only way how to do it is testing. You have to try, you have to test it, and every time try to understand why it's behaving in such a way. So every time I do performance benchmarking against, some performance benchmarking on maybe some different machines that I don't know, because we have a performance lab, in-house. So if I'm benchmarking in AWS, so I start small. Then adding the load, I'll see where I'm hitting the ceiling actually, and then I can decide based on that, based on my knowledge of the software, I can decide what's the optimal load that will actually produce me good results, and I will be testing the feature that I'm implementing. So every time, please try going slow, understanding the results step by step, and you will also understand your software from a performance point of view much better. Let's go to another one. When we had our first anniversary, I didn't forget, by the way. I didn't forget, but we went on a ball. And I got so drunk that I wasn't able to dance through the night. And she was expecting that. And since then, I was always a perfect gentleman on all the anniversaries, all the birthdays, and whatnot. But she forgets this all good, and she takes the bad. Yeah, my fault, I know. So, so the thing is that she's actually throwing away information. And that's That's the next problem that I want to describe. Now, so we started with, we know whether we're testing throughput or latency. We now know that we have to think about the load that we're pushing into it, pushing on the system. And now let's focus on the latency tests. So I see that the typical things that you can do is that the measure latency of each operation. And very often I see this thing that we collect all shitloads of operation, and then we show to the product manager, to ourselves or somebody, only an average. In a very bad case, only an average. Then somebody shows, minimum, maximum, and an average. Still, it's still pretty bad. Still not enough information. Even better, they will show you the percentiles. Okay, the 50 percentile, 75 percentile, 90, 99, 99, 99, etc. Okay, better, still better. Even better, we can do to show the whole latency distribution, the whole histogram, to get the full picture. And I'm saying this is still not enough. And by the way, like 90% of people that I saw doing performance testing were not even showing the full latency distributions. So can we do even better? Can we actually show more information? Let me show you some computation, or show you the properties of that of those averages, min, max. This is actually an arbitrary data set because I didn't want to make it too big, but I've seen performance test results that were actually like this, then mixing. So you can see that from the data set A, the average is 16, and at B it's 12. So A is worse, let's say. And then with the minimum, A is better. And then with the maximum, B is better. And then P12, P20, P50, P80, A is better. But P90, B is better. How can you decide which one is better? How? I don't know, because you cannot. That's the thing. You have to specify your requirements, and even better, you should see the whole latency distribution. So let me show you. This is you don't have to really understand all the details, but these are the percentiles. In Hazelcast, we only care about the highest percentiles, but we can also generate the lower ones. But in here, this was actually the optimization that I show you in the step 1 where they did a time sliced round robin optimization. So it actually drastically improved the latency against that the state before. So I see the distribution of the latency. I see the 99 percentile is somewhere there, whereas for the red line, the 99 percentile is way above. So I see immediately that the blue line is much better from the latency point of view. This gives me the full picture. I'm not losing any information. I'm not forgetting about any goodness that he brought me the flower. Okay? And I'm saying, can we do even more? Because this is what histogram is containing all the information. So what am I saying to get even more? And the thing is that when you look at the chart, this is a summary. This is a histogram at the end of the whole test. Does it show you that? Can it show you that there's actually something wrong going on from, let's say, latency point of view, from performance point of view? No, you cannot see it because you see, okay, the 90 percentile, it looks okay-ish, let's say. But if I, from the same run, if I chart the latencies, this is the 50 percentile evolving over the time. So 50 percentile at 10 seconds, 50 percentile at 20 seconds, 30 seconds, etc. So I see the percentiles actually growing, developing all the time. And in here, I immediately see that the latency is growing over time, over the period of the 2-minute test. So this signalizes a problem, right? And we're all Java developers here. So what might be the obvious root cause of kind of system slowing down continuously? Garbage collection, right? Garbage collection. This is when I look at the chart, my first candidate is garbage collection. So let's look at just to prove myself. Let's look at another chart which proves this was the GC statistics of the young space during that run. It was actually memory leak. But I wouldn't have got that from this chart. This looks legit to me. This looks perfectly legit. So the takeaway, another takeaway from this problem, from this issue, is to not throw any information. If you have the information, don't throw it away. Use it. Generate all the charts that you possibly can. Throughput, latency, system statistics, collect it. Memory management, network statistics, CPU, GC info, whatever. Collect everything, and then look at everything. Like just you will get the pattern. You will get the pattern. You will know where to look at after some practicing. But if you're serious about the performance testing and performance, you have to understand what's going on underneath. And for that, you need as much information as possible. A great tool for this is HDR histogram. It's a library written in Java by Gil Tene. He's a CTO, C-something-O of Azul Systems. Great guy, one of my heroes. I would love to meet him if he's here. No, he's not. And he wrote this HDR histogram library, which helps you compute all the percentiles from your data set and some other nice things. So this is definitely a great tool to have or to use when you're serious about latency measuring. I will also mention his presentation at the end of the talk, which is very great about latency testing. Okay, problem number 4, an unexpected operations ratio. For this one, I have no good metaphor for my fiance, so sorry. And the things like that. We have our system, and it usually can do more than one thing, right? Typical reads and writes. And we get the, let's say, customer scenario that we should test this, and they tell us that, okay, we have 80% of gets and 20% of puts. This is, by the way, typical caching scenario in the distributed system, and this is very often a requirement. So we want to test this scenario, set up the test, and we'll see how the testing the optimization, let's say, or customer fix based on on their particular use case. And what we might do, what might happen, is that we accidentally end up with a different ratio that we wanted to. How? You might, not because I'm an idiot, but maybe and I am. So the test setup, the first thing that might come to your mind would be to set up 100 clients, 80 clients just doing reads, read, and 20 clients doing puts. Obviously 80-20 ratio, right? However, the operations usually, or not usually, they don't last the same time. They don't have the same latency. So for illustration, you have the read to take just 1 millisecond and write 2 milliseconds. So it's 2 times slower. So let's do some math. Let's do some basic elementary school math. So the read client does 1,000 operations per second. The write client does 500 operations per second. So let's run the test for 5 minutes, shall we? So 1,000 times 60 seconds times 80 clients, we have 24 million operations, reads. And then we get 3 million writes. If you divide it, the end ratio is 80. It's off by 10%. And obviously, the longer the test will run, the bigger the difference will be. So this is maybe something that you might not expect. Like it's trivial when you see it. It's completely trivial, and we can all go for a beer. But I wish that somebody would have told me some of those things 3 years ago. By the way, the takeaway, it might be a complete valid scenario. It might be that your customer, your user, is actually using it in such a way. That's perfectly valid scenario. However, sometimes it's not, and usually, from my experience, it's not. There's just a client doing puts and gets or reads and writes based on the current workflow or whatnot. So the first thing that you can do is to actually get more information about the scenario and make sure that this is what they really want, what you should really test. Or, if it's not what you should really test, you can do a fix to your benchmarking tool that you can generate the operations. You can make all the clients equal and generate the operations based on probability. You know, like a random in divided modulo something. You know, some very simple thing. But all the clients are then equal, and you will actually get much closer. You will get to the ratio that you actually wanted. Cool. So that might be another thing that, you know, might not be so obvious. Now it's obvious, but I was really surprised one time when I look at the absolute numbers. So, and the last problem is performance regression, and I would end it with a metaphor. You know, I think going back to your ex-partner is a really bad idea. So that's just my opinion. And and with performance is even worse, because this is the worst thing that you can happen. You're developing a new shiny 2.0 version. Somebody installs it, and the performance is like 10% lower. So that's something that's not nice, and especially if you're focused on the performance. If your software is wrapped up around performance, just like the Hazelcast one is. Customers are unhappy. They are pretty angry, actually, and it's not a nice mindset to go back instead of going forward. So how to avoid it? Obviously, you have to test it. You have to continuously test your software, you know, and I will show you just how we do it. But the solution or the takeaway is you have to pay attention to it. You have to, and the right way, or I think the only way that works, is to automate all the stuff, because nobody will ever, like, you know, I can tell you to run the performance test every day and then look at the results. Nobody will ever keep up every day, or run it in the different scenarios. You know, you have endless numbers of scenarios. So the key point here is the automation. And once you actually do the test, you store the results. You don't just have it on your local machine, you know, stored in an Excel file or a CSV file or something like that. You actually should store it somewhere so you can come back to that in the future. If you don't have the history, you cannot claim the regression, obviously. So and check the results on a regular basis, or even better, automatically. I can show you just a short preview, short demo of the application that we use for storing and analyzing performance test results. Let me just look. Yeah, I'm still at the PN. Perfect. So this is an application that we call PerfRepo, Performance Results Repository. And here you have, these were just like configuration issues, so don't pay attention to it. But here we have a history over time of for instance, of the scenario with throughput one with the 100 kilobyte values. And we store it. These results are somewhere from December, when I did it in the JDG in Infinispan in Red Hat, and then I brought this to Hazelcast as well. So we can immediately see whether the regression is happening or not. On the right side, you see the drop. I can immediately see that something went wrong, so I go there and investigate. In this case, this was a friendly colleague executing something on the machine while this is running automatically. And this is all running automatically every day. You know, we have the continuous integration tools and your benchmarking, and just if you automate everything, it works. If you and then you pay attention a bit to it, but you have something to actually back up your claims that you're not hitting the regressions. We also store the results. Oh, okay. I need to just relog. Okay, and we store the results. We tag it so we can actually find any result in the past. So just a quick demonstration. If I want to see the results for 3.11 version, I will just search by text and say that is an arbitrary text that you can, customize it to your wishes. I recommend using something like that, or thinking about preparing yourself to prevent performance regression, because that's not something that you want to have. All right, let's move. These are some of the useful resources that I think that are very useful. The first one, Gil Tenner's presentation, How Not to Measure Latency. Absolutely brilliant, brilliant presentation about measuring latency, about the caveats of it, about a big problem that I didn't mention here because it's a separate presentation actually done by Gil Tenner. Coordinated omission problem. So I recommend you, if you're interested in it, watch that presentation. It's a 1 hour long presentation or 2 hour long in Hebrew. So suits your needs. Also, Optimizing Java, pretty nice book with all the also some kind of low level stuff about the JVM, but not that much. And the really low level thing, System Performance by Brandon Gregg. That's pretty. For me, it was the hardest one to read. Since I have still some time, because when I'm a bit nervous, I speak faster. So I actually prepared a bonus slide. I was thinking about that. So so a short quiz, just a very short quiz. This is the test setup. We have 2 servers, 2 clients, all in separate machines, whatnot, and the client is sending values, like a put request via REST or via our protocol, with different value sizes. Like these are 3 scenarios: 1 kilobyte, 10 kilobyte, and 100 kilobyte values. We measure it, okay, perfect, and we get the throughput results. So for 1 kilobyte we had 100, approximately 100,000 operation. For 10 kilobyte we had 10,000, 11,000 operation, and for 100 kilobyte values we get like 1,000 and something. So when I look at the results, where you look at the results, this is question for you. So do you see anything strange? Are those results correct? Any ideas what might be wrong with this? Sorry? Performance is dropping on 1 kilobyte. That might be actually like it's still kind of because you have 10 times larger value and you have 10 times lower throughput. It kind of makes sense, approximately. Exactly. So the answer was, we're actually not testing the system, but we're testing the network. Because what do these numbers look like? They are too perfect. It scales too perfect, And this is the biggest takeaway I can give you, that if something looks too perfect in the performance testing, it's usually wrong. It's like you always have to think whether the numbers add up. So it scales. I get 10 times bigger value and I get 10 times lower throughput, and 10 times bigger value and almost exactly 10 times lower throughput. In this particular case, by the way, this issue was found during the setup of the performance regression testing environment. So it was too perfect, and we found out that the machines that we were executing it on had only 1 gigabit network card. And if you actually multiply the numbers, it's 1 gigabit. The basic. I should have a small b there. Sorry, but. The basic math will prove you that you're actually hitting the ceiling. Then you can confirm it with other tools like nload. You see the full saturation of the network. But in the first, when you look at the numbers for the first time, you'll go like, okay, this is pretty sweet. Yeah, we're really good. Hazelcast is scaling linearly. No, it was a mistake. And of course, when you think about it, it doesn't make sense because when you, for instance, when you're sending 1 kilobyte values, You open a socket, send a kilobyte value, close the socket. Open a socket, send, close the socket. And you do it 100 times more than in a 100 kilobyte value scenario, right? The opening and closing happens only twice, whereas there it happens like 200 times. So that's, it's all connected. And I think that one of the biggest, the most important things in performance testing in general is when you get the results, sit for a while, look at the results and think. Really think if they make sense, if the numbers add up, if it's behaving as you would foresee, as you would expect. Because it's very often that the numbers just don't add up, and you must not accept the numbers just because the test was successful. Green tick and Jenkins or something. So that's my message to you. I think this was exactly how I wanted to plan it. So that's all from my side, and I'm ready for questions if you have any. Okay, sure. Yes. Right. Okay, so the question was whether, I guess you haven't heard it, so the question was whether there is any open source project like the dashboard that I just showed for storing the and analyzing performance results, and also for storing micro benchmarking, also integrated with Jenkins somehow. The question is yes, and it's this tool. It's open sourced, by the way. It's named Perfrepo. I was developing it in Red Hat, and I actually didn't provide the link there because I'm a bit ashamed of the documentation right now, because it's still in a work in progress. But we use it. We use all the main parts. How it works? It's a simple web application. It's basically Postgres database storing there. It has no notion of understanding the results. Actually, it just stores the number value there, and you have a REST client where you create those entities and you send it to that web application. So you can actually store anything you want there. You can actually bend it through different requirements. When I was developing this in Red Hat, I was spreading this Perfrepo usage tool usage, and in the end, it was before I left, it was 14 different teams using it, so it was very flexible. But yeah, I could definitely use a contributor because I'm really not able to keep up right now with the development, because right now it has all the things that I need. But we can definitely, you can ping me on Twitter. We can work something out. I will be happy to get you engaged with. Any other questions? Okay, there's something on the ceiling, I see, okay. In that case, yeah, sorry?
Do you use some kind of tools which measure the overall performance of a system? This way you can detect some saturation of CPU, memory, network, or something like that.
I see, okay. In case of Hazelcast, we're doing a library. We're developing, IMDG library. So we're not having an actual system. We're not doing any, end application. So we have our proprietary testing tool, suited for our needs. But we measure all the things like, but we're not running anything in production. I mean, this way. But there's this, for instance, Apache JMeter, and Gatling, and how is it called, the last one? I will remember afterwards. So there are a number of tools. I know that there are a number of tools, but I don't have any particular experience because I was always working with the lower level of the system. So we were measuring the more isolated part of the system. Sorry. Sorry? Edmond?
So Edmond is a Unix tool that gives you an overview of the CPU, the disks, the network, and that can stream the measures over time so that you can record them and see the evolution over time.
I see. Okay, cool. Yeah, but I don't have any personal experience with that. Sorry. But you know, the methodology applies still the same. It's about using a different tool suited for your needs. But these are the things that you should not forget or should be aware of. Sometimes there are perfectly valid scenarios. I already got two. Okay. Yeah. Another question.
Do you think it's a good point to measure the power consumption of the devices?
If I think that it's good to measure
The power consumption.
the power, sorry?
Power consumption.
Oh, yeah, of course. You mean power consumption? Okay. I guess it depends on your use case. We seriously we don't care about power consumption because we are not running the software, so we're not paying for the electricity. Yeah, but what we actually measure is the utilization of the machine, right? Because that can transform into the power consumption. But yeah, you should measure anything that's important to you. I'm talking about performance, but if memory management or memory statistics are important to you or some other stuff, you should definitely measure it. But these are like the things, the methodology of that can be applied also to different measures. But no, we're not running any application. We're not running any servers. We're buying them from AWS, for instance. And when we have some of the in-house performance testing labs, we're happy to spend the money on it because that's all we care about. Yeah, it's an interesting thing. I have never thought of the measuring. Can you do just like in a house? You would type down your state of the electricity measurement, and then. Yeah, I don't know. No, I have no experience with that. Any other question? Okay, I guess that's it. Thank you very much. Enjoy your beer.